Good morning, Krusty Crew. It's not morning.
Oh, yeah. I'm feeling kind of crusty.
It isn't helpful.
Yeah, your puppies are a lot older.
It's 4:30. All right, so let's
A lot of
start.
art taken care of.
So I just moments before class posted everything that's current at the moment, all the notes, all the links to the YouTube. So today's assignment, problem 5 is due, practical midnight, and the problem set 6 is now available, due in a week. And then we'll have fall break, and we'll take a break, and there won't be homework over fall break, so, yeah. I'm a man of the people. Right.
Will it be posted over fall break or not till after?
We won't have a problem set until the Tuesday after fall break, due the following Tuesday, so.
We'll have a break.
Thank you.
Okay.
September? No, October.
No, there's, many breaks. Yeah, that's November.
We had a full week?
No.
No, it's Thursday, we always take off Wednesday, because you got to travel on Wednesday, and then but we also have Thursday, Friday off, so.
Oh boy, 3-level Adam.
Yeah, all right, oh boy, back to our regularly scheduled program. So we're starting to talk about 3-level atoms. For example, the so-called lambda configuration, which just means that the shape of this thing looks like the letter lambda in Greek. And this is also known as a Raman transition, which was a late 19th century thing about Raman scattering. We'll talk maybe a little bit about that in a moment. But we have 3 levels here, and in particular, we have it such that, say, level 1 and level 3, there's an allowed, for example, dipole. It's an allowed dipole transition. There's a dipole matrix element between level 1 and 3, and there's a dipole matrix element between 2 and 3. But in that case, we wouldn't have an allowed dipole matrix, electric dipole matrix element between 1 and 2. For example, these could be 2 different magnetic sublevels within a manifold of the electronic ground state. Okay, so in, say, an alkali atom or hydrogen-like atom, and these 2 would be metastable states. They would be, and there would be no, they would say both be S states, and there'd be no electric dipole between them. And this is, say, a P state, an excited state. Yeah, no.
For 2-level atoms, do you always have a dipole transition between 2
No, I mean, what we said is that's the dominant. I can have a 2-level atom between 2 levels that have no electric dipole between there's no electric dipole matrix on between them, but then the Rabi frequency would depend on a different multipole. For example, I could have an S state and a D state, and then it would be a quadrupole transition. It's a very weak transition. That matrix element is small, which would mean the electric field I would need to drive that would be, I'd need much stronger electric field in order to drive that transition. Or it might be a magnetic dipole transition. For example, these 2 states could be separated by the hyperfine splitting, and say this would be, say, the clock transitions in an atomic clock. And that has a magnetic dipole, but no electric dipole. So I could, in principle, drive the transition by some other field that is resonant between them, but it would not be, it would be a weak transition. So for example, in say atoms where we're storing quantum information in the clock states, often we could drive that with a microwave, and it's the magnetic field that drives that transition. But that microwave transition, I can't then look, it's got such a long wavelength, I can't focus it to focus down on one atom. If I want to drive that transition, drive it faster, I would typically do it with a 2-photon transition. Yeah,
For the homework that's due tonight,
yeah,
did you want us to do the adiabatic elimination?
I
or
did.
Just, okay, I did.
it's in the notes and you can just copy it.
Okay.
But I want you to go through it and remind yourself how it goes. Yes, indeed.
Okay.
Good. So, right, so this is the configuration. Typically, this excited state has a finite lifetime, and the lifetime is 1 over the rate of emission, but there's typically a branching ratio where this can spontaneously emit, maybe with some rate to level 1 and some rate to level 2. The total rate of emission or decay, spontaneous decay, is the sum of these two, okay? So we've defined, in this case, the detuning from the excited state. Here, the way it's defined is it's the difference between the laser frequency. This is a 2-photon, 2 different colors, okay? So there's 2 photons that are associated with this process, and this is seen to be off resonance, say, for absorption of laser 1. So that's the definition that we're giving for the detuning. It's always the laser frequency minus the resonance frequency. So that's always our convention. So if it's positive, I'm above resonance. If it's negative, I'm below resonance. And then there is a 2-photon detuning. So this difference between the frequency of laser 1 and laser 2 is sometimes known as the beat note. If I were to look at them, there would be an envelope that would beat at this difference frequency, okay? That difference frequency might be 9.28 gigahertz, right? That's a microwave, and that would drive, that beat note is a microwave that would drive this transition, and the difference between that beat note and this resonance is the 2-photon detuning. Mm-hmm.
So you have underneath omega L1 minus L2, you have delta omega L. Is that a subscript or multiplication?
Where?
Right. Sorry. Yeah, the definition of delta. Oh, there's too many. Little delta.
Little delta. So I have, this is the difference. I'm saying this is the beat note.
Is that omega? Is that delta sub omega or?
It's delta omega laser 1, 2. It's the difference. I'm just defining as the difference of those two frequencies.
So delta is in the difference.
It's just the difference of those two frequencies. Okay, it's the beat frequency, which is whatever it's beating to be near to that. Okay, it's not necessarily exactly that. The difference between the beat note and the resonance frequencies I'm calling little delta. It's the 2-photon detuning. Okay. Sometimes known as the Raman detuning, but I'll explain why there's so many notations here, okay? And then, as I said, there is a dipole matrix element between, say, level 1 and 3 and level 2 and 3, and there's an associated Rabi frequency, which is the dipole matrix element dotted into the strength of the electric field. So there's an electric field associated with laser 1 and the electric field associated with laser 2. Okay, those have different, whatever amplitude they have, that determines the Rabi frequency. Okay, so that's what we talked about last time, and we discussed last time. I'm not going to go through it again. You're going through it, or you've done it, handed it in already. We can adiabatically eliminate the excited state when we have a separation of time scales. So when the detuning and or the rate of spontaneous emission is huge compared to the Rabi frequency and or the detuning, the 2-photon detuning, then we can adiabatically eliminate the fast variables that adiabatically follow the slow variables, which are, in this case, the amplitudes associated with these levels 1 and 2. And it's a way of getting another way of getting an effective two-level system. So we're back to where we started. And as I said, one of the motivations for this might be I want to drive Rabi oscillations between level 1 and 2, and I want to do them fast, but I can't because there's no matrix element. I don't have a dipole allowed transition, so that's a small matrix element. And so if I want to drive, I could do it with, let's say, a microwave, but that's just going to be, that amplitude is just slow. The Rabi frequency would be slow. Mu dot B would be slow compared to D dot E. So going through this 2-photon rate is a way of doing it faster, and it's also a way of, I can use lasers to individually address the atoms. Yeah?
Does it also allow us to then have our state 1 and 2 both have a much smaller spontaneous emission?
Yes, that is also true. I mean, these, indeed, and we'll come back to that, the coherence time of this two-level system is much longer than the coherence time of this, because this has a very short lifetime, whereas if I'm sufficiently far off resonance, and that brings me to the next point, which we discussed at the end of the last lecture, which is just thinking about adiabatic elimination in the context of a two-level atom. Yeah?
Is it worth trying to think about the Bloch sphere for just pairs?
It is. So we'll talk about that. Okay, I want to emphasize, and you make a good point, but I want to re-emphasize it. Once we have a qubit, we got a qubit. We don't care where it came from. It's a qubit. It could be the dual rail qubit. It could be the polarization qubit. It could be the clock state qubit. It doesn't matter. It's a qubit. Once I got a qubit, I got a Bloch sphere. And we use it all the time. Okay? So it's a pseudo spin. It's a spin up, spin down. It doesn't matter what it is. We just map it to that. All right? Good. All right. So with that said, we were talking about, at the end of last lecture, the case of just thinking about adiabatic elimination in the context of the two-level atom. Okay? So when we have the two-level atom, this is my effective Hamiltonian. I've written down, this is the Hermitian part, and then the excited state has a finite lifetime. And because it has a finite lifetime, we can just treat that as having an imaginary part to its energy eigenvalue, which determines the rate of decay. Okay? That won't be trace preserving, but we can always put back in, as you are doing or have done already if you've done the homework, the refeeding term by hand to make the master equation for the density matrix be trace preserving. But we can learn a lot by not worrying about all that and just thinking about it where we think about it in terms of a Schrodinger equation for with a non-Hermitian Hamiltonian. We learn a lot by doing that. And so we did that in this case, and what we found after we did the adiabatic elimination is that my state here, I have a state which is evolving as a function of time according to this effective Hamiltonian. Of course, it's not going to be norm preserving because I didn't put the refeeding term in, but I'll live with that for the moment. And this state has an amplitude in the ground state and an amplitude in the excited state. And as we showed at the end of last lecture, after I did the adiabatic elimination of the excited state, I got an equation of motion for how the ground state evolves. And what we find is that there is a phase shift. So if I were to ask what is the ground state amplitude as a function of time, it gets a phase shift that's determined by this term, and the amplitude decays by that rate. That is the solution. Of course, this is not the exact solution because over some time, eventually, there will be spontaneous free feeding of the population into the ground state. So this is only true for some amount of time where I can neglect that refeeding. okay? Which is to say, I can neglect this, okay? But what we see, importantly, the thing to focus on is what the heck do these two things mean? This term, what I'm calling delta EG light shift, is the energy level shift of the ground state. It's the fact that I have an interaction between the laser, the D.E interaction, the dipole interaction between the dipole of the atom and the electric field perturbs, that's my signal for being perturbed, by the field, and it shifts the energy level. The ground state is shifted by the light, hence the name, the light shift, okay? Also known as the AC Stark shift. It's called the AC Stark shift because if you remember the Stark shift from standard quantum mechanics, when you look at, say, the hydrogen atom in a DC electric field, the energy level is shifted due to the interaction of the electron with the external field. This is the interaction of the valence electron with the oscillating electric field. And with all rotating wave your hands, you get this, okay? And so that's the light shift, and it has this form which is related to the saturation parameter. Remember, S is the saturation parameter. Which is approximately this if delta is much, much bigger on far resonance. So that's where this came from, okay? And this term, we said, is the photon scattering rate, which is also the rate of absorption. So population leaves the ground state at this rate, which is the rate at which photons are being absorbed. That's why the amplitude in the ground state is decreasing, okay? The scattering rate, we should also remember that in this same limit, if I'm too far from resonance when S is small, that this is the population in the excited state, right? In steady state, we solve the optical Bloch equation. So the scattering rate can be thought of as the rate of emission from the excited state, which is the probability to be in the excited state times the rate of spontaneous emission per atom in that state. Yeah?
So then you're saying that just so I'm understanding correctly, you're saying that the scattering rate describes both the rate of emission and the rate of the concentration.
Because in steady state, they're the same thing.
Yeah.
Everything that's absorbed is emitted.
Yeah.
So the absorption rate is the emission rate. Okay. Now, the other thing we talked about last time is thinking about dress states. And I just want to, again, remind us about that. So when we looked at, this is what the zero got. This is my interaction Hamiltonian. So this Hamiltonian came from D.E in the rotating frame. Let me rewrite. This is not a good way to write. So in the rotating frame, we have this. And this is the bare Hamiltonian. This is H0, and this is the interaction Hamiltonian. this H0 was the Hamiltonian, the bare Hamiltonian of the atom in the rotating frame. That system. This is my d-d interaction. So if we looked at the energy eigenvalues, which we can easily do, because I can rewrite this as h bar times minus delta over 2 times the identity times h bar, the total dotted into sigma, where h effective, omega effective is the Rabi frequency in the x direction minus the detuning in the z direction. Then that told me that the eigenvalues of this are h bar omega over 2 times the minus sign plus or minus h bar over 2, the magnitude of this, which is the square root of omega squared plus delta squared. So those are the eigenvalues of the atom dressed by the photons. Okay? And so what we saw here, if we look at this, let's just look at this first of all. If I look at this, the way I've chosen it, the ground state has 0 energy. So let's first, here I am for positive detuning. This is the ground state at 0 energy. Here's the excited state down here. This splitting is the detuning. This is for blue detuning. These are the bare states without the light on. When I turn the light on, these are the states. They're split, in this case, by that. In blue detuning, the ground state is shifted up. The excited state is shifted down. For red detuning, the opposite is true. Here's the ground state, and here's the excited state. The ground state is at equals 0, and the excited state is at E equals h bar times the magnitude, because minus delta is a positive number, right? So this splitting is the detuning. And now when I turn on the light, this is split by this amount. For red detuning, the ground state is shifted down. And so the difference, the shift, the light shift of the ground state is generally equal to minus h bar minus, so for red detuning it goes up, for blue detuning it goes down, so it's plus the sine of delta times h bar over 2 square root of omega squared plus delta squared.
Those are the same picture.
I think G and E are switched.
Oh, yes, you're right, genius.
In this case, in the rotating frame, this is above, and this guy went down. So this splitting is equal to minus h bar. If I factor that out, the magnitude of delta times the sine of delta is h bar delta times 1 plus omega squared over delta squared to the 1/2 power. So in the limit that I'm far detuned, which is to say the magnitude of the detuning is big compared to the Rabi frequency, this is equal to that.
So is it very close to 0? Very far into?
That's correct, but it falls off like 1 power of the detuning, okay?
So,
And so I can compensate for that by having this be sufficiently strong.
okay, so I know maybe my undergrad physics
Yes.
in here.
Uh-huh.
So if you had a really high detuning, I have this misconception. It's like, the light is invisible to the atom.
Not completely.
So that's a misconception, right?
Yeah, I mean, this is a wrong thinking that I only absorb if I'm exactly on resonance. there's some amplitude for absorption on resonance, and it falls off. The population in the excited state here so this is the population in the excited state in steady state. It falls off in this way, it goes to 0. I have very little absorption, but it's not completely invisible to the atom, okay? And importantly, and we discussed this briefly at the end of last lecture, again, I want us to focus on this. This is the phase shift that's induced, that depends on the light shift. Notice its dependence on the detuning. This falls off like 1 power of detuning, whereas the scattering rate falls off like what power? Falls off like 1 over the 2nd power. This is related to the fact that if we look again at the polarizability falls off, the imaginary part falls off like 1 over the square, whereas the real part falls off like 1 over the 1st power. So if I'm far away from resonance, then I can see very little absorption with some amount of refraction. The refractive index is basically the light shift. The fact that I have an induced dipole moment which interacts with the field gives me an energy. And I can have it when I'm sufficiently far off resonance that the reactive term is much bigger than the absorptive term. And that's how we trap atoms, neutral atoms, in light. We do it way far off resonance, but with enough intensity to make a big enough shift. So if I have, as we discussed at the end of last lecture, if I have a laser beam which has an intensity profile, remember the Rabi frequency is proportional to the amplitude. The Rabi frequency squared is proportional to the intensity. So this is the intensity as a function of, say, the transverse direction of the beam. The intensity is highest in the middle of the beam, weakest outside the beam. And so if I were to look at this as let's call this direction X, the transverse direction. If this is the intensity as a function of X, what does the light shift looks like as a function of X? Well, the light shift, we just said, is proportional to the intensity. But it's proportional to the intensity times 1 over the detuning. If the detuning is positive, well, it just is like this, but if detuning is negative, that's if I'm of resonance, then this is my light shift as a function of X. At different positions, it sees different intensity. And so the atom will be sucked into the regions of high intensity and will be trapped there as long as its temperature is low enough that it doesn't just fly out. You gotta cool it down, otherwise we're gonna fly away. Yeah.
So the way you just, excuse me, when you talk about dress states and how like,
Yeah.
in the presence of the field, it, shifts the energy.
Yeah.
Is this an application of the AC Stark shift, or is this a different thing?
It is the same thing.
It is the same.
The Stark shift is the light shift. They're just different names for exactly the same thing. The energy level is shifted. This state is called the dress state, which I'll call G tilde. G tilde itself is a superposition of the bare ground and excited states, because it has some admixture, really superposition of excited state. The ground state is now polarized. It has a dipole moment. And the strength of it, and what's this theta? Well, theta is the direction of the spin of the eigenvector, which depends on the direction of this vector. Remember, the eigenvectors of this Hamiltonian are spin up and spin down along this direction on the Bloch sphere. And that direction on the Bloch sphere is determined by the relative, it has, arctangent of this. So theta is the arctangent of omega over delta. And when this is approximately omega over minus delta, when this is big. So if this is a small number, then this is 1, and this is theta over 2. So this is equal to omega over minus 2 delta. So my ground state has a little bit of excited state admixed in by this amount. The ground state is perturbed. The ground state, and if you did perturbation theory, which I know you guys did, you can find the perturbed eigenstate by the appropriate, you start with the 0th order eigenstate and you add the matrix element over the, that's this. And if you did problem 3 and problem set 4, which you should have done, it was extra credit, but you should do it anyway, then that's what you find. Okay? So this is one way to induce a phase shift on a level, is to light shift it a little bit. Turn on the laser, off resonance, turn it off, and it will accumulate a phase. And the phase that accumulates is this. It's equivalent to what we saw before from far off resonance during Rabi oscillation near the South Pole, right? But this is it's the adiabatic picture of the same thing. All right. So, with all of that said, I want to return to the 3-level atom, which you guys just did for homework, so that saves me a lot of work. I don't have to do anything. Except find the damn thing on my notes. Because I write. Do. All right, I should have. I don't care here. Let's go back. Reload. Oh, I'm not on the internet. It says who? Oh, here we are. Okay. All right, lecture 8.
Yeah, I want coffee.
Just gave me an excuse to drink some coffee. All right. So, let me start here. So, when we looked at this Hamiltonian with our interaction, so we have our 3-level atom. So our atom, there's some energy of the level 1, there's some energy of the level 2, there's some energy of the level 3. This is my 3-level system, and this guy has a finite lifetime. So that's my bare Hamiltonian with an imaginary part. My interaction Hamiltonian is minus d dot E, where my electric field has 2 colors. It has frequency 1 and frequency 2. So that's my Hamiltonian. The bare atom and the dipole interaction. We restrict the dipole operator to these 3 levels. These 3 levels, it only has dipole matrix elements between 1 and 3 and 2 and 3, but no dipole matrix element. We go into the rotating frame. We make the rotating wave approximation. When that's all said and done, we get the following Hamiltonian. So in the rotating frame and the rotating wave approximation, my effective Hamiltonian with the imaginary parts and all, becomes the following. Minus h bar delta minus I gamma over 2 times level 3. And minus h bar little delta times level 2. I take the energy of level 1 to be 0. I can define the 0 of energy anywhere I like. That's where I choose it to be. H bar omega over 2. So this should look vaguely familiar. If I just had level 1 and 3, it would look like that. If I just had level 2 and 3, it would look like this. The only difference now is I have two terms that cause Rabi oscillations, right? Between levels 1 and Rabi oscillations between level 1 and 3, and Rabi oscillations between level 2 and level 3. And I have this extra detuning term here, okay? So this is my effective Hamiltonian, and when we then look at the Schrodinger equation for the state under this non-Hermitian evolution, when I write the state as having amplitudes in all 3 levels, then I get these differential equations, which are just the equations for those amplitudes from the Schrodinger equation. So what these equations, you should stare at them a little bit to understand what are the different terms telling me, okay? It's not just a bunch of gobbledygook. You should just look at oh, that's what this term means. This is just telling us there's Rabi oscillations between level 1 and 3. I see similar Rabi oscillations between 2 and 3. There's the effect of the detuning, which gives a kind of phase here. But 3, Rabi oscillates both to 1 and 2. And then there's this term, right, which has to do with the decay and the detuning. So get a feeling for what all those terms mean. What do they look like? So again, the magnitude of this complex number is chosen to be huge compared to these numbers. In which case I can do the adiabatic elimination, which is to say this basically comes to steady state well before any of these guys change at all. And when that's true, I can just set that derivative to 0 and do the adiabatic elimination. And that tells me that this guy, as a function of time, is equal to I omega over 2 C1 plus I omega 2 over 2 C2 divided by I delta minus gamma. So now this variable is now slave to these slow variables. It's come to steady state. That's the adiabatic elimination step. Okay? And so then I plug that back into the equations for C1 and C2. I've now gotten rid of C1 and C2. And then, when I do that, I get the following after some algebra. So I'll define all these things in a moment. Let me just write down the equation. So much notation, so little time. All right. So once we've done this, let's look at these equations now and try to understand. Let's first define what all these different terms are. We've defined these before. This is the light shift. So delta E light shift for the jth level is equal to h bar times delta over 2 times the saturation parameter for that level, okay? So let me just make sure I got this right. Yeah, so remember the saturation parameter in this case it's the square of the Rabi frequency over 2, the detuning squared plus gamma squared over 4. So there's a saturation parameter which tells me how much I've saturated the transition between level J and the excited state. So there's a saturation parameter for level 1. Level 1 could be saturated, and there's a saturation parameter for level 2. Given that, there's going to be a light shift. So level 1 is going to be light shifted by some amount. In this case, it's going to be shifted down because it's ready tuned. That depends on the detuning and the Rabi frequency, okay? So level 1 will be light shifted a bit. In addition, level 1 can absorb or scatter photons. And so there's a photon scattering rate associated with each of those levels, which again is the saturation parameter for that level over 2 times the spontaneous emission rate. Everyone clear on those two terms? That's what we just did for the 2-level atom. We see exactly the same terms that we see before, okay? There's this additional term that's due to the 2-photon detuning. And then finally, we see what? Let's forget about this. What does this thing mean? What does this term with this do?
Oscillation.
It's a Rabi oscillation.
Right?
Just like we said before, we looked at those terms. There's a Rabi oscillation between level 2 and level 1. Level 2 and level 1 are now Rabi oscillating between one another with a Raman Rabi frequency. And the Raman, get all this factors correct here. The Raman Rabi frequency is omega 1 times omega 2 times delta over 2 divided by delta squared plus gamma squared over 4. Okay. In addition, there's an effect by which the coherence between 1 and 2 is decaying. It's the Raman decay rate, which is omega 1 times omega 2 times gamma over 4 delta squared plus gamma squared over 4. Okay? So, putting those two together, you can get an equation of motion for the density matrix the elements of the density matrix are related to the amplitudes in this way. The diagonal matrix element is the square of the amplitude. The off-diagonal elements are the coherents. So if I took the time derivative of this, I'll get this dot times this, plus this times this dot in using, and if I put them together, I get the equation of motion for the density matrix that looks like the Schrodinger equation, but with weirdness. Instead of the regular old commutator, I have the dagger. That is the Schrodinger equation, but with a effective Hamiltonian that has an imaginary part. This is not trace preserving because we didn't put in the refeeding. But I can add in the refeeding term by hand, and then I'm done. And if you've done it, the homework, I hope you have, you've done it. Okay? That's what you have to do. Okay, but now let's revisit these equations. I want to revisit these equations for a moment. And in particular, I'm going to be bad and I'm going to erase this because we know what these things are. Let's consider the limit where I'm far detuned. Adiabatic elimination does not require me to be far detuned. I could be right on resonance. I can have delta be 0 as long as my Rabi frequency is small compared to the spontaneous emission rate. I could do that too. But I can also think about the far detuned limit. And when I have far detuning, then my magnitude of my detuning is very big compared to the line width. That corresponds to, as we were saying over here, being far detuned compared to the line width. Okay, so I'm way out here. In that case, then we have that. Remember, the light shifts scale like 1 over the squares of the detuning. The scattering rates and the Raman decay rates scale like 1 over, no, this goes like 1 over the detuning, this goes like 1 over the square of the detuning. So in the far resonance limit, at least for a good amount of time, I can neglect these terms. That's just the limit of having coherent oscillations. Okay. So, in that limit where I'm far of resonance, then what do I have? In that case, I have, so I'm going to set this guy to 0 as well. I have Raman Rabi oscillations. If I looked at how the coherences change as a function of time, if I put all that together, I get the following thing. Minus I delta Ram I'm just looking at one of the coherences. The other one is just a complex conjugate of that. And then we can look at the equation of motion for the populations, okay? But I want to focus on how the coherence is evolving as a function of time. Let's go back to this board again and remind ourselves what we're doing. We're shining light that of 2 colors that's near resonance for this transition and this transition. If I just had a 2-level atom, that would drive coherence between, say, level 1 and level 3, or coherence between level 2 and level 3. But through this process of adiabatic elimination, look what we have done. We have now coherence being driven between 1 and 2. 1 and 2, there is now coherence being generated between them. There is a Raman-Rabi frequency, which is here, which is approximately equal to omega 1 times omega 2 divided by 2 delta magnitude, right? Well, and actually there's no absolute value here. Could be, the sign should be there. It's not so important, but the major point here is the following. I now have 2 photon-driven Rabi oscillations. We have now been able to drive Rabi oscillations between level 1 and level 2 with a Rabi frequency that's given here. The Rabi frequency depends on the product of the electric fields of the two divided by the detuning, okay? So if I go far off resonance and I want to make this pretty good, I better focus my laser pretty hard to make the intensity a lot stronger in order to compensate that, okay? So you really got to crank up the volume. I've heard there's a new Spinal Tap 2, this one goes to 11 again. I don't know if you guys are old enough to remember that. But yes?
So is it the same story with the population too then? Because I couldn't have population go from 1 to 2 before, but now, since they're coupled together with the Raman oscillation.
So I will absolutely, I should have, these are exactly the optical clock equations that we had before, except we have now a different Rabi frequency. And the final thing I haven't written down is, what is the detuning? So if you put all this together, what you find is delta Raman, the Raman detuning. So this is the Raman-Rabi frequency, and this is the Raman detuning, is equal to delta minus delta light shift 2 minus delta light shift 1. So let's think about what this means. Let's go back to this picture again. Suppose that little delta were 0. That is the case where I've chosen the beat note to be exactly equal to this Bohr frequency, okay? The question is, am I on Raman resonance? Am I on 2-photon resonance? The answer is not necessarily. Why? Because level 1 and level 2 are light shifted. So this guy is shifted a little bit off resonance, and this guy is shifted a little bit. If that shift is not the same, I'm not going to be on 2-photon resonance anymore. Which is kind of a problem for Raman transitions because your laser amplitude is never that constant. It always screws up. It's varying in some way, which means you're going to get some dephasing. You're going to get T2. T2 is, remember, because the energy levels are shifting a little, you're going to get a dephasing. So you got to do a spin echo to get rid of that. That's why you learned all that stuff, because that's what you got to do in order to get rid of that problem. Okay? Yeah?
This density matrix that you're describing on the left there, is that a 2x2 describing only states 1 and 2?
That's correct.
Yeah, okay.
So the important point here was this. When we can do this adiabatic elimination, we remove the intermediate state and again describe this for all intents and purposes as a new 2-level system. It's a 2-level system where coherence is being driven between them. Of course, it's going intermediately through the virtual excited state, because what the heck does that mean? I don't want to come back to that. I hate that term. But ultimately, I'm driving coherence between these two levels. It's a two-level system. It has its own density matrix. And the equations of motion are, again, Larmor precession of a torqued a pseudospin on the Bloch sphere with a certain detuning and a certain Raman frequencies. In addition, there's decoherence. In addition, there's loss, and that loss is due to the photon scattering, the absorption and emission of photons, and there's an additional effect that's due to the Raman coherence being damped. And so I will never have perfect coherence in driving this Raman frequency. So if I wanted to do a quantum logic gate as a Hadamard between these two things, my logic gate will be fundamentally limited by how far off resonance I am. And so, in fact, it's an interesting point. Yes, just a little side. So, you guys, I don't know if you read the news about, IonQ just got $1 billion or whatever for making an ion trap quantum computer because they just bought Oxford Ionics. Why did they do that? Well, it's because the way Oxford Ionics works actually is they drive this with an actual magnetic field that's a current near that's oscillating at gigahertz frequencies that makes a, remember, oscillating currents make a magnetic field. And that magnetic field drives this, and there's no spontaneous emission, so they can have much higher, fidelity gates. They now have 4 nines of fidelity in their gates because they're not using lasers, they're using electronics and the magnetic fields to drive those.
Why does a
Continuum?
why does a microwave? Why can you? I know there's no transition between 0 and 1.
There is.
Why does a microwave?
There is a transition. It's just it's a magnetic dipole transition.
There's a magnetic.
It's a magnetic dipole.
So when you use laser,
It's the magnetic field of the. Remember, an electromagnetic field is electromagnetic. It has both an electric field and a magnetic field. It's the magnetic field oscillating at microwave frequencies that's driving this transition. Not the electric field.
And with lasers, the magnetic field is very strong.
Typically, well, typically the strength, the much stronger coupling is to the electric dipole, not the magnetic dipole in the multipole extension. Yes.
So right now we're talking about the Bloch equations for 1 and 2 and the adiabatic elimination.
Yep.
Does it make any sense to look at, say, the Bloch sphere for 1 and 3 and 3 and 2 and how they correlate and
I mean, when we went to these equations, there is no separate Bloch sphere for just 1 and 3 and just 2 and 3. They're all coupled together. So when we have the 3-level system, really, we lose this loveliness of having an easy visualization of the evolution of the state of the system as moving on some nice manifold. If we could do it, we could write down a generalized Bloch sphere, but it would be in multi-dimension, it wouldn't be a sphere anymore, and so we never do that. All right, we have more to discuss today. So I want to come back to this equation. I'm going to write it over here on this board. Okay, so after adiabatic elimination, we found that the probability amplitude in level 3, according to that equation, I'm going to write it down again. Let me just try to find it and copy it over here. Is equal to I multiply top and bottom by minus I. So it's omega 1 over 2. Let me get my notes so I don't have to keep going back and forth over here. Bless you. Some people are more sophisticated than say sometimes.
Pretentious is the better word.
Yeah, that was the other word I was looking for.
No, it's not the plague anymore.
It's insight.
Is that the real word? Bring out your day.
Yeah.
All right. So, this is what we found. Okay. Now, interestingly, there is a specific case where, so we can find a state. Suppose that this amplitude is actually 0. Is there a solution to this equation where the probability amplitude in the excited state is actually 0? Sure. That is true if the ratio of C1 over C2 is equal to minus omega 2 over omega 1. So, for example, that state, I'm going to define a state that I'm going to call the dark state. This state is called the dark state. It is your father.
Drop a square?
Square. Why is it dark? Yeah.
No population.
Was that?
No population.
There's no population. So in particular, let's look at the case where I'm right on resonance. It doesn't really matter. Okay? So I have 2 lasers. I shine one of them with the frequency laser 1 that's on resonance between 1 and 3, and another guy that's on resonance between 2 and 3. Okay? And suppose that I prepared the system somehow in this superposition. So suppose I was initially in this superposition with some amplitude here and some amplitude here, with this particular phase relationship between them. The claim is if the atom is in that particular superposition, it can't absorb the light. It is dark to the light. You're dark to me, all right? And there's an amplitude C1 and an amplitude C2 associated with that, which means that there is destructive interference between these 2 histories, these 2 possible ways that the atom can absorb. There's a destructive interference because of this minus sign. So this is a purely quantum effect. No classical description of a Lorentz oscillator can show this. This is a quantum interference effect. We can see this explicitly by calculating, let's again look at my interaction Hamiltonian, which in the rotating frame was omega 1, 2, 3, 1 plus omega 2, 3, 2 plus the information conjugate, which I will appreciate. Right? That's my d dot e interaction in the rotating frame. We got that. Okay? This is my atom laser interaction. We would say the rate of absorption, if I started in this state, this dark state, would be proportional to the matrix element just by Fermi's golden rule. Right? That's the ground state, the initial state, that's the final state. What is this matrix element? Let's calculate it.
In this case, should be 0.
It should be 0. So generally speaking, let's just say I have some arbitrary ground state, just to calculate what this is, which is some superposition of 1 and 2. I don't know what it is. Let's just say I have some superposition, and let's calculate this matrix element. Okay, what is it? Well, it's equal to the matrix element between the ground state and the excited state is equal to h bar omega 1 C1 plus h bar omega 2 C2. But by definition, that's 0. That's what this equation tells me. This equation says omega 1 C1 plus omega 2 C2 is 0. Everyone see that? This is the same on both sides. Omega 1 times C1. And so, if I'm in the dark state, this amplitude, this superposition, destructively interferes. And I have no absorption. That's called the dark state. There's another way to look at this. Which is, let's again look at this interaction Hamiltonian. And I'm just going to rewrite it in the following way. Take a look at that. Tell me if you agree with that algebra. Right? I just multiply top and bottom by this, and then just, but look what this is. This state is the thing that's orthogonal to that state. This state is the bright state.
In my head, I was going, I swear, if you call it the bright state.
So there is a bright state which is coupled, and so if I started in level 3, I'm going to Rabi oscillate between level 3 and this superposition. With no coupling, the bright state and the dark state are a different basis. So I can think about level 1 and level 2, or I can think about the dark state and the bright state. When I turn on the laser, I only am coupled to the bright state. I am decoupled from the dark state. Even though it's a 2-level system, there's only one state in this Hilbert space that I'm coupled to. These two guys are orthogonal, the dark state and the bright state. And I Rabi oscillate at this frequency. Yes?
Should that not be the bra upside of bright, or is there something on this?
Yeah, it should be the bra.
Thank you.
So, again, It's a two-level system. I'm Rabi oscillating between 3 and the bright state with no coupling to the dark state. Now, if I start in level 1 and have no coupling, and that is, of course, a linear combination of the bright and dark state, right? And I have to think about the matrix elements between all of
So
those.
there's different representations to make a qubit.
That's right.
That's beautiful.
There's lots of them. Now, let's look at this again. I have this guy, say I'm right on resonance. Okay, now of course we know that there's also, if this is a dipole allowed transition, there are also spontaneous decay, okay? So suppose that I'm driving the system in this way with these, whatever Rabi frequencies I got that depend on the dipole matrix element and the amplitude of the field. This thing is going to Rabi oscillate, but it's also going to decay. What is the steady state of the system after all is said and done? Well, in fact, if I just had a two-level system, and I just had one, and I drove this in steady state, there'll be some population in the excited state, some population in the ground state, and some coherence between them. The amount will depend on the Rabi frequency, and in this case, gamma, because my tuning is 0. But what do you think the steady state is here? Yeah.
Perhaps maybe a population inversion.
Well, you never get, no, that would be beautiful. It'd be great if that happens and you can get a laser. That's a different story, lasing without inversion. But no, I don't get a population version. The dark state, in fact, in steady state, that's an excellent intuition. Why is that a plausible thing? Because if the population ever got there, it would stop. All dynamics would stop because it can't absorb any more light. It's done. It's dark. It can't go anywhere. And this phenomenon was discovered by actually Alain Aspect before he worked on, whatever the heck, Bell's inequality, whatever the heck, Bell's inequalities, the thing that got him the Nobel Prize. And this is what's called coherent population trapping. Or as the French like to say, CPT. That's exactly how they say it. And what it's a phenomenon whereby you're shining light, you're having all of this spontaneous emission. But through this dissipative process, the steady state of the system is one where there is coherence. The steady state is a superposition, a coherent superposition of these two sublevels, these two, we call them both ground states, even though one might be low because they're the electronic ground state. And this is a way of preparing a superposition through optical pumping. Okay? Yes?
Well, like, what good does it do if I can't talk to it anymore?
Well, that's an interesting question. I wouldn't be able to talk to it through the process of this kind of absorption, but I might want to use this ultimately, say, for an interferometer of a different kind where I talk to one state or another. It's a good point where if it's dark and it seems it's dark to me, you're gone. right? But indeed, I might want to prepare. It's also a very useful phenomenon, as I just kind of rediscovered yesterday in the context of laser cooling, because there's something called velocity selective coherence propagation, or VSCPT, where the process by which I fall into the dark state only happens if the atoms are really cold. So if they're moving, they won't fall because of the Doppler shift. So it's a way of collecting atoms into a very, very cold spot through dark states. We'll talk a little bit more. There's some very interesting aspects of this ability to manipulate coherence in this way, quantum coherence in this way, through the phenomenon of destructive interference. You should really think about the dark state as an interference phenomenon. There are two processes which can cause the atom to absorb, and this destructively interferes with that. That's what this is telling us. All right, to be continued next time. Yeah.
Absorption from
Yeah, the Ramans.